In this video, we will be discussing hypothesis testing. Often when analyzing data, you will need to make hypotheses about population parameters and their true values, and then test these hypotheses. Generally, you will be deciding between two hypotheses that are the opposite of each other, meaning one must be true and one might be false. These are the null and alternate hypotheses, where the null hypothesis is denoted by h sub 0 or h naught, and the alternate hypothesis is denoted by h sub a. And the alternate hypothesis always carries the burden of proof, but we'll get back to that. So the test procedure for a hypothesis test looks like this: 4 main steps. First, you state your hypotheses. These may be given to you in the problem statement, or you may have to generate themselves from what the problem is telling you. Second, you calculate your test statistic from the data. Third, you find your rejection region. And fourth, you state your conclusion. So we'll go over these steps in this video. So the null hypothesis is your prior belief hypothesis, what was initially believed to be true and what must now be tested. This hypothesis is assumed to be true until proven otherwise. It's like the American justice system. This hypothesis is your defendant. They are innocent until proven otherwise, or in this case, true until proven otherwise. The alternate hypothesis in that example would be the prosecutor. The burden of proof is on them. It is contradictory to h naught, and in a good hypothesis test, all possibilities are covered. For example, if the null hypothesis is that the true mean is equal to 0, then the alternate hypothesis could be the true mean is not equal to 0. So those two hypotheses are mutually exclusive and collectively exhaustive, which, in case you need a probability refresher, means that they cover all possible outcomes and there's no overlap between the two of them. So your test statistics are a calculated quantity from the sample data, and it's used to make conclusions. So they're going to be a z or a t test statistic based on the distribution and the amount of data. The formula for those, for the z, looks like z equals to x bar, which is your sample mean, minus mu, all divided by the sample or the population standard deviation divided by the square root of n. Your t looks very similar in that it's x bar minus mu divided by the sample standard deviation divided by the square root of n. So we'll get into a little bit of how to tell whether to use a z or a t test statistic. So your rejection region is going to be the set of all values for which the null hypothesis will be rejected, and it's determined by the alternate hypothesis. It's based on if it's a two-tailed test, a lower-tailed test, or an upper-tailed test, and the significance of the test alpha, which in most cases is 0.05. So a lower-tailed test has an alternate hypothesis that looks like this. Mu is less than or less than equal to mu naught. And mu naught is typically the value in the null hypothesis, where your null hypothesis says we think that this is the true value of mu. So mu naught is normally some real number. And a fun trick to remember if what you're doing is a lower-tailed, upper-tailed, or two-tailed test. A two-tailed test is pretty easy to remember. It's the non-equal sign. It means you have two rejection regions on either side. Each one of them is has the area of alpha over 2. So when you add them, there's a combined area of alpha. But for the upper and lower-tailed tests, you'll notice that the upper-tailed, the greater than sign, looks like the upper end of this normal graph, where the lower-tailed test, this less than sign, looks like the lower-tailed of this graph, which is just an easy way to remember what you're doing. So your alternate hypothesis determines your rejection region, along with your test statistic Z or T sub alpha, or Z or T alpha divided by 2. So if your calculated test statistic falls within one of these shaded areas, you're going to reject the null hypothesis. So should you use a Z or T distribution? So if your data is normal and you know the population parameters, use a Z-test. This is very similar to very similar to confidence intervals and prediction intervals. If the data is not normal or not specified as normal, but n is greater than 40, you can also use a Z-test. And lastly, if the data is normal, but sigma is unknown or it's less than 40, then you use a t-distribution. So there are two possible outcomes of a hypothesis test. One, you reject the null hypothesis, the alternate hypothesis is true, or you fail to reject the null hypothesis. You can't prove that your alternate hypothesis is true. This is similar to going back to our justice system example or metaphor. This is similar to a not guilty finding. You're not saying the defendant is innocent, you're just saying we can't find him guilty. So there's not enough evidence to convict, or in this case, reject the null hypothesis. So when you're conducting a hypothesis, there are two types of errors, type 1 and type 2, as they are aptly named. Type 1 error is equal to your alpha probability. It's rejecting the null hypothesis when it's actually true. A type 2 error, also called beta, is failing to reject the null hypothesis when it is false. So it's debated which of these is a more serious error. I would argue that it depends on the context of the problem. Most often, type 2 error is slightly worse than alpha, or type 1 error, excuse me. So let's look at some example problem statements to see if they would be a Z or a T test. So first, the calibration of a scale is checked by weighing a 15 kilogram weight 25 times. If the results of different weightings are normally distributed with a standard deviation of 0.2 kilograms, the test if the scale is displaying accurate results or not. So for this example, we know they're normally distributed, and we know the standard deviation. So we're going to use a z-score for critical value. And a sample hypothesis for this would look like the null hypothesis might say that the true mean of the readings is equal to 15. And the alternate hypothesis could be that the true mean is not equal to 15, and this would indicate that the scale is not accurate. It is not displaying the right weight consistently. So next we'll look at second problem statement. A certain brand of battery is marketed as having a lifetime of 800 hours. Suppose you want to test the company's claim that this is true. A random sample of 50 batteries is used. So it doesn't say what distribution this is from, but the random sample is greater than 40. So we will use a z-score, and we will calculate the sample standard deviation for them. And you could test, again, similar hypotheses. Let's say you think that the company is making an outrageous claim and these batteries only last for much less than 800 hours. In that case, your null hypothesis would be mu is equal to 800, the prior belief that they're marketing, and your alternate hypothesis would be that the true mean is less than 800. So you'd be trying to prove that the true lifetime of the batteries is less than 800 hours. using a z-score. Lastly, we'll look at a third example problem in an experiment design to measure the reaction time of humans to a certain stimulus. The sample average time for n equals 8 subjects was 4.32 seconds, with a sample standard deviation of 1.43 seconds. It had been previously thought that the reaction time was at least 5 seconds. Do the results of this experiment contradict prior belief? So in this case, we know that n is much less than 40, but we know the sample standard deviation and the sample mean. So we use a t statistic, a t critical value, and this problem is an example of one that really sets up your hypotheses for you. So you'll note that it says prior belief. It had been previously thought that the reaction time was at least 5 seconds. So in that case, your null hypothesis would be that the true mean is equal to 5, and your alternate hypothesis would be that the true mean is not 5. Or in this case, you could also do the true mean is less than 5. So more information on this topic can be found in your textbook, Probability and Statistics for Engineering and the Sciences, the 8th edition by J. Devore.